The next question is again from Pathfinder, and it's a very beautiful question. I really liked the solution given in the book for this question. So we'll do it by two methods. The first method we'll do it by taking a charge. Basically, he's asking the potential. I'll explain to you the question. So that way, the second we'll look at the solution given in the book, which floored me. It was really good. The solution was very good, and I liked it a lot. So let us discuss both these solutions. So what is asked is there is a semicircular ring, okay, and it has a what do you call linear charge density lambda naught sine theta, okay, and he's saying there is a point here, some random point here, some p, and he's asking the ratio of the ratio of potential at the center O to the general point. So what is the ratio of potential here to the potential here? That is what he's asking. Okay. So fine, we'll just take this radius r, and we know the potential due to a point charge, that is kq by r. And so let us take a point charge here. This is very small, okay, this d theta, and this is dq, and I'll take this distance as some. Let us find what this distance is. So this is r, this is dq. So due to this dq here, what is the potential? Tell me. I'll just write it here. dv equal to k dq divided by this distance. So what is this distance? Tell me. In this triangle, root over r square plus r square minus 2rr cos theta. Okay. So this distance we have found out to be this. Now we'll just write the terms. What is dv? K. What is dq? Tell me. Lambda times r d theta, that is lambda naught sine theta into r d theta divided by root over r square plus r square minus 2rr cos theta. Okay. Now yes, we can take this term as some t square. Well, let's just simplify this now. We can take this term as t square. What will we get? R square plus r square minus 2rr cos theta equal to t square. And so again, if you differentiate this, you will get 2rr sine theta d theta equal to 2t dt. Okay, 2 cancel, and now let us just put it here. It becomes pretty simple. So what do we get? Let me put this here. dv equals to k lambda naught sine theta. See, this r sine theta d theta, r into sine theta d theta will become t dt divided by r. Okay, divided by this is t square anyway, so this becomes t. You can cancel out these two. We get this as k lambda naught by r dt. Okay, we just integrate this. This is anyways a constant here. So we integrate this overall from theta equal to 0 to. Okay, so when theta equal to 0, theta is 0. What is this t? Tell me. When theta is 0. So this is r square plus r square minus 2rr, that is r minus r. 2, when theta is 180, this becomes r square plus 2rr cos theta. Becomes r plus r. So what will this become? K lambda naught divided by r into r plus r minus r minus r. Okay, so that is k lambda naught by r. This becomes 2r. So that is 2k lambda naught. Okay, so this is the potential at a general point. Now, what is the potential at the center? Tell me. Potential at O equal to k total charge divided by r, because all the charges are at a distance r here. So k integral lambda naught sine theta d theta r d theta divided by r. Okay, I can just cancel this r and v at o comes out to be integral sine theta d theta 0 to pi comes out to be 2, so this comes out to be 2k lambda. So at o it is 2k lambda naught. At some general point here also it is 2k lambda. So what is the ratio, tell me? Find the ratio. Ratio is 1. Okay, so that means either I'm here or anywhere on this line, the potential anywhere on this line is the same, and it is equal to 2k lambda. Okay, so this is the solution that we have looked at. Now let us see the solution that was given in the Pathfinder, the hint there. Okay, so this is the very beautiful intuitive solution that was given in the Pathfinder. So what you do is you consider a uniformly charged sphere. Okay, and this is our x-axis, x, y, and this is the z-axis. Okay, this is the z-axis. Now what he's doing is similar to how we have a semicircular ring here. He's taking a strip here. Okay, and on this strip he's taking one element. You see here, this angle is phi, angle with the x-axis is phi. Okay, and this is a d phi here. This is a z-axis, and angle made by this with the z-axis is theta. Basically he's calculating a dq here. Okay, see here, what was dq? We wrote here dq was, this dq was what, tell me? Lambda naught sine theta into r d theta. This was the dq here. Now let us see if there is something similar here. So this is d phi. I want to find what is the dq here. Okay, dq here is what, tell me? Surface charge density sigma into the small area, this dA. So dq equal to sigma into what is this area right now here. You see this part, this vertical part which is there here, this is theta and this is theta, so this will be r d theta, this vertical part. Okay, so r d theta times, now what is this part here? Okay, you see this one is r sine theta, because this is theta, this is r sine theta. Okay, and here we have moved by d phi, this is also moved by d phi here. Okay, see, because here this whole thing was r d phi was very big here. As we are coming, towards the center here like this is becoming smaller. So this is also d phi. Okay, so r d phi has become smaller and smaller, and so this length is r sine theta into d phi. R sine theta into d phi. For all the charges that we are taking, small charges that we are taking here, this d phi is the same. Okay, so what will this dq be, tell me? Dq equal to sigma into, let us see here. So here we have dq equal to lambda naught r sine theta d theta. Okay, and see here also sigma r square, okay, d phi into sine theta d theta. Okay, you see this whole term sigma r square d phi which is there here, this is some constant. You can think of this as lambda naught here, lambda naught r here. You see sine theta d theta. Here the total charge will come here if you are integrating theta from 0 to 180. Here also the total thing will be covered if you are integrating from 0 to 180. So basically he's saying that the strip on a uniformly charged sphere is similar to what he's asking in the question. Okay, so we know that due to this whole sphere, if it is a hollow sphere, at this point here, what is the field, tell me? The net field is 0. Suppose due to this strip here, the field is in this direction. At some general point, it is in this direction. Which means due to a strip, exactly opposite strip, the field has to be in this direction from symmetry. Right? So if it is in this direction, what would be the net field direction? Net field direction will be like this, due to all the strips. But we know that inside a hollow sphere, the net electric field is zero. So there is no electric field, which means all this should be zero. The whole electric field due to this here must be zero. If the net electric field due to this here must be zero, that means the potential must be the same everywhere. So on this diameter, anywhere you take, the potential must be the same. So this is equivalent to this, is equivalent to this. Okay. So this was a very beautiful, intuitive solution. Okay. And I think even in the JEE advanced exam, when the professors are giving the questions, they would have done a lot of work behind it. There would have been hours and hours of thinking, and there would have been some thought process behind giving that question. So what we do is we have some general methods and we try to solve the question and we solve it. But if JEE Advanced, the professors for at least a few questions, they give the thought process, their unique thought process, or what triggered them to give that question, that would be a really nice thing for the teachers, for the students, to see this new thought process. So this was something really beautiful. I've seen in a very long time. So do this question, and some more questions if I get like this, I'll share with you.